Hello everyone, my name is Tobias Puls, and this is work done together with Rasmus Dahlberg. We are both at Karlstad University, Sweden. I'll be presenting our work on website fingerprinting with website oracles, starting by giving a background to Tor, then introducing website oracles, followed by website fingerprinting with website oracles, then a brief presentation of different sources, and wrapping up with conclusions. To begin with, what is Tor? Well, Tor is both a web browser and a network. In terms of a network, it's a low latency anonymity network consisting of around 7,000 volunteer-run relays or servers around the world. Users, on the other hand, of Tor typically interact through or with this network through Tor browser, which is a web browser, a fork based out of Firefox. You can use Tor browser to browse the web anonymously, to access so-called onion services, and also circumvent censorship. In this presentation, I would like to focus on the use case of browsing the quote-unquote regular web with Tor browser, although our work to a degree also applies to onion services. When you browse with Tor browser and visit a website like petsymposium.org, Tor creates a circuit through the Tor network, starting from your Tor browser, to try to obfuscate your identity online. These three hops, these three relays, have particular roles, are selected in an intelligent way, and it's not that important in our case, except knowing that the first entry of this circuit is called the guard, and the exit is, well, called the exit. It's the last one, and there are about 1,000 exits today in the network. We know that Tor browser has around 2 to 8 million daily users, depending on which measurements and how you measure, I guess, but at least million of daily users. And thanks to a study by Mani et al. In 2018, we know that the websites that are visited by users of Tor browser map very well to the so-called Alexa top 1 million most popular websites online. So in other words, we know that the users of Tor browser visit basically the same websites as, say, a Chrome user or a Safari user. This detail will matter a lot later. Since Tor is an anonymity network, the literature is filled with a wide range of different attacks on Tor, and of course Tor's design aimed to mitigate a lot of them. One particular type of attack is a website fingerprinting attack, in which a local passive attacker, such as your internet service provider or your router or, say, your network interface card on your computer, looks at the encrypted traffic from your Tor browser of you as a particular user as it enters into the Tor network, and based on the patterns in this encrypted traffic, tries to determine which website you're visiting on the web, just based on the encrypted patterns. Attacks are surprisingly good at this, in particular if you consider deep learning-based attacks. It turns out that recognizing patterns of network traffic, encrypted network traffic, is similar to, say, detecting phases in images. So deep learning is very good at this. We have studied website fingerprinting attacks in literature for, well, in the ballpark 10 years or so, and there are many challenges for an attacker in practice to perform these kind of attacks. Too many to touch upon here, but for example, imagine if a website fingerprinting attack, or a classifier, since it's typically a machine learning classifier, tells an attacker that Alice, this particular user we're monitoring, she visited example.com. What does this really mean? In the sense that, can the attacker really trust this classification? And the answer to this is that it really depends on so many things. Among other things, it depends on what's called the base rate, meaning that how often is Alice really visiting example.com? Maybe she's simply not interested in this kind of website at all and would never visit it. So that means that any even the smallest false positive rate, so any false positive from this classifier, in general observed in experiments or as we evaluate it, would mean that actually from the attacker's perspective, when the classifier says Alice visited example.com, it will be useless. It would always be wrong. We've had these kind of debates in the website fingerprinting community for quite some time, and as luck would not have it, we've had quite a similar debate in society at large the last half a year or so around how effective COVID-19 antibody tests are. What does it mean for an individual contra what does it mean for the population, for example, right? So we're all familiar with these kind of problems, unfortunately. And a similar debate has been raging for quite some time in the website fingerprinting community. So one of the motivations behind our paper is that we wanted to look at if we could make the situation a bit more clear up this debate a little bit, and as in make it clearly the case that this is not a huge issue for the attacker. And the idea we want to do this is by making the attacker stronger, slightly stronger, by introducing these website oracles. And we don't want to make the attacker too strong, like a global passive adversary, because then we know that it's outside of the threat model of Tor. But it's going to be somewhere in between there. And I hope by the end of this presentation, I've convinced you that an attacker that has access to a website Oracle and tries to do website fingerprinting is more like the website fingerprinting attacker with, say, a credit card than it is a nation-state actor acting as a global passive adversary. Well, let's see. And this leads us on to website oracles. And a website oracle, just like an encryption oracle or a decryption oracle, for those who are familiar with encryption security notions, is an abstraction. And it's an abstraction of a capability that we believe is reasonable to assume that our attacker have somehow, but it's an abstraction, and it's going to be a very powerful one. And then we're going to look at how to realize this abstraction later on in the presentation. So a website oracle is available to a website fingerprinting attacker as follows in the modified figure that I showed you before. Where the attacker can ask the website oracle a question and get a yes or no answer back. And the question that the website oracle will answer for the attacker is if a particular website was visited by someone at a particular point in time through the Tor network. And I want to emphasize here that we are talking about some time frame, typically in our paper in the orders of milliseconds, hundreds of milliseconds, but could also be seconds. And it's for a website, a particular website, but it could be for someone, meaning that it could be anyone from the Tor network visiting this particular website. So one way to look at what the website oracle does is that it performs a membership query on the destination anonymity set of all possible websites that are visited at a particular point in time by anyone from Tor. This kind of abstraction is actually quite easy for us to simulate. We can simulate it. And once again, we're going to be leaning on the Mani et al. Survey I mentioned earlier before, where they performed a privacy preserving measurement of real Tor network traffic. First, we learn how websites are distributed, approximately. And by websites being distributed, I mean how are they visited, and which websites are visited through the Tor network. And there are two ways to look at this, the data we get from this from Mani et al.'s work that are useful for us today. And one is to say that, okay, about 1/3 of the traffic goes to Alexa Top 1000, 1/3 goes to the rest of Alexa Top 1 million, and the remaining or last third of website visits go to other websites that are not on Alexa Top 1 million. Another way to look at it is that 40% of the traffic from Tor, or the website visits, I should say, goes to Alexa Top 10,000, and 60% to the rest. So okay, we have an idea now how website visits are distributed, thanks to the work of Mani et al. It's a long tail distribution, right? Most people visit the most popular websites on the web, and the rest is just a bit of noise. We also learn from Mani et al. A quite good upper bound, I would argue, of the number of website visits that take place per day through Tor. And we know this through their measurements of the number of initial streams per circuit. They did a measurement of about 104 million website visits per day with a 95% confidence interval. We take the upper bound of this confidence interval and assume 140 million websites that are visited through Tor for a full day. And we assume that this is uniform, perhaps naively. But because we now have the number of website visits through Tor, and we know how they are distributed, we can make a simulation of the entire recipient website anonymity set I showed you in the previous slide, and that gives us a way to simulate a website oracle, since all it does is query this anonymity set, right? So I'm now going to convince you that having access to such a thing, to such a website oracle, is ridiculously useful for an attacker, and then hopefully I can also convince you later on that it's not overkill, it's not too much. So in a website fingerprinting attack, an attacker monitors m particular websites in what's called the open world. So maybe it monitors, say, Google or Facebook, for example. And when a victim visits a website, we assume that either the victim will visit the monitored website, so for example Google or Facebook, or it might also visit an unmonitored website, let's say Pet Symposium. So this gives us this terminology, monitored or unmonitored, in an open world. In the paper, we define two verifiers that can be used together with any website fingerprinting attack. We define a binary verifier and a list verifier. The list verifier is just a binary verifier in a loop. Please see the paper for that. But the binary verifier is quite simple. So if the website classifier says that a monitored website was visited, such as example.com, then we say that when we have access to a website oracle, we only accept that positive classification that a monitored website was visited if, when we ask the website oracle, they confirm that this monitored website was visited. If the website oracle doesn't confirm it for us, then we will classify it as unmonitored, even though the website fingerprinting classifier said it was monitored. Clearly here, website popularity of the monitor websites is very important. Because as I mentioned, let's say you want to monitor access to, say, google.com or facebook.com. Most of the time, there's going to be somebody through the Tor network visiting these websites because they are so popular. So the website oracle will always confirm gladly a classification for google.com or facebook.com. So in this case, the website oracle is useless because it will always say yes, 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 yes to the question of these popular monitor websites being visited. So in this case, a website oracle is, you might as well not have one. It's useless. It's just a function that returns true for you all the time. But when you visit less popular websites that are less frequently visited through Tor, then there will be cases when the website oracle rules out what would have been a false positive from the classifier. And this is when the website oracle shines. So we are going to be altering the popularity of the monitor websites in our experiments now. I'm going to show you 9 graphs now, quite rapidly, but they all look identical. We just change one thing mainly. On the left-hand side, let's focus on that one. We see a precision recall graph, as is typical. We see one line for DF. This is for deep fingerprinting. It's a state-of-the-art deep learning-based website fingerprinting attack. And then we have 5 more lines, ranging from 1 to 10,000. And these 5 lines represent using deep fingerprinting with a website oracle, where you are monitoring websites that are at the Alexa popularity rank 1, 10, 100, 1,000, or 10,000. As we can see on the left-hand side here, website oracle access makes precision of the classifier very, very good. And it also slightly improves recall. When we move on in this new setting, where we give the attacker access to a website oracle, we also see that against the defense walkie-talkie, we can improve the precision dramatically. Similarly, we can see for WTF pad, a huge increase in precision as well, and a slight recall increase as well. Moving on to constant rate defenses with significantly more overhead, we see similar things here. So for CS Buffalo and Tamara, we see a huge increase in precision, but we can only ever so slightly improve recall. So the gain of the oracle is that the classifier will not give a false positive, even though these attacks these defenses are in place. However, the defenses are still very effective because they reduce recall to ridiculously low levels, especially for Tamara. Last but not least, we can see the same thing with the 2 configuration of Dynaflow. Precision is very, very good as soon as you hit somewhere around Alexa rank 100 to 1,000, always at the very top for 10,000 as soon as there is any recall. But yeah, false positives are reduced significantly, almost close to perfect, especially for higher Alexa ranks. So we just saw that simulated website oracles are very effective at reducing false positives. Let's look at how to concretize website oracles. Where can we get one? What are potential sources? In the paper, we enumerated a large number of sources and evaluated them through some metrics, which unfortunately I don't have time to cover now. But I would like to highlight 3 or 4 sources that we think are particularly troublesome. To begin with, content delivery networks like Cloudflare make perfect website oracles. On the right-hand side here, we see an approximation for the number of sites, or I should say, sites on the web, which are protected, quote unquote, by Cloudflare, and they are in the tens of percentages here. It's not the Alexa rank, but it's something probably quite similar. Should mention that Cloudflare has a convenient API to their customers with the nanosecond precision in the logs that are retained for days, according to the retention policy. And on this topic, it's worthwhile to highlight that website oracles can be used retroactively, right? You don't have to have this capability in real time, inline. Many sources, such as Cloudflare, can be used after, retroactively, to confirm a classification. Another particularly troubling source is real-time bidding. There's a great article by the FF that covers how, in particular, Google is at the center of this. But the gist of it is that when advertisement is shown by Google and other big players online, there is a network of advertisement providers that are given information about this ad that is about to be shown, and they're allowed to bid on it to show this ad to you. And this kind of process takes in the order of a few 100 milliseconds. And having the ability to sit at this table to observe offers of showing advertisement, or actually showing the advertisement to begin with, or buying access to this, is also a great website oracle source that I would encourage anyone with more insight into real-time bidding to dig deeper into. Last but not least, we have DNS. And from DNS, observing DNS requests, we can map this precisely to websites we know from earlier work. So to begin with, DNS servers are used by exit relays in the network to resolve domain names, right? And we know that many exits use DNS servers from Google or Cloudflare. We did a measurement for a couple of days on our own to get these percentages on the slide. We also observed that RIPE Atlas nodes are available in the same autonomous systems as about half by bandwidth of all exit relays in the network. So if you cannot query Google or Cloudflare, you could query the DNS servers directly used by exits in their autonomous systems if they use the ISP provided ones. I'm going to show an example of this very soon, but I just want to also mention in the context of DNS, when we have the big picture here, that each exit in Tor also has an internal DNS cache, and you can query this cache with the relay resolve command. And basically, if you get a fast response to this, it means that something was cached. If you get a slow response, it means that the domain name you're querying for was not cached because they have to go and ask their DNS server. And this is also a website Oracle source, which we experiment with in the paper. But moving on to the DNS servers, or going back to, I should say, to the DNS servers that are used by exits. Here I am from home querying Google's DNS server 8.8.8.8. The domain name or subdomain here be dragons of a domain name we control, which is configured to have a TTL of 900. Once we query it at home, we see that, okay, we get a response back and it has a TTL of 899 seconds. If we then wait a couple of seconds, like half a minute or so, and we query it again, then we see that the TTL is much lower than what is set in the record, in the A record. Now it's 847, which implies that somebody visited or requested this DNS domain name some time ago. This is also a website Oracle source. And this is how you could use a DNS server of an exit to find out if this domain was ever resolved and therefore a website was visited. I would also like to mention the fact here that domain servers from like Google and Cloudflare have some sort of probabilistic at times shared cache globally. So actually, there are some domain names you can query globally if they're cached or not. But please see the paper for some more details there. So to quickly conclude, we responsibly disclosed our results to the Tor project and to researchers in some of the researchers in the community. We had some discussions, and eventually we landed in that this work went public during December last year. The Tor project posted a blog post on how they view this kind of new attacks and what they think are good mitigations. I encourage you to read it. Most importantly, I would want to say that they encourage research on defenses, which I think is a wise thing in general for website fingerprinting. If we look at our question or the issue with website fingerprinting we looked at earlier around the base rate, and we consider this outcome of a classifier, but this time a website fingerprinting with website Oracle classifier saying that Alice visited cow.se. Well, in this case, for most websites and most website visits in Tor, this means that the classifier is right. Alice did visit cow.se. And we accomplished this by using the base rate of all users of the network against the victim, whose base rate might be very low as well. We ran an experiment where Alice never visited the monitor website in question. And we put the monitor website at Alexa popularity 10,000. We then observed a false positive rate in the order of 1 per millionth monitored website visited by the victim, I want to emphasize here, which results in a very low false positive rate. And this rate will be even lower for less popular websites, which is the majority of websites online. If you recall the number from before, about 40% of website visits in Tor are made to Alexa top 10,000 websites. So our conclusions are that website fingerprinting, website Oracle attacks are a real threat, at least in the sense that they address this base rate argument, this base rate challenge for website fingerprinting attacks. Oracle's addressed this at least for most monitored websites and for most website visits done over Tor, as the measurements tell us. There are some key limitations in our work, of course. We only do website and not web page fingerprinting, and everything is simulated. We've done some experiments, some network measurements in the paper on Oracle sources, but in most parts we are simulating things, of course. One thing that we are also simulating in the paper are imperfect sources for website oracles. For example, the website Oracle could have a false positive rate, right? But I encourage you to see the paper for this. It does not change the picture much, unfortunately. One potential mitigation for website oracles is to hide when a website visit takes place, but this is extremely costly to do for an extended period of time. So I'm not sure this is a worthy defense direction to go into. When you're constructing and evaluating website fingerprinting defenses and attacks, I would urge you to consider the maximum possible recall you can get, because false positive rates will go down with website oracles significantly, so precision is a less useful metric. My personal take is that website oracles are scary. Deep learning is even scarier to me. And I personally think we need efficient and effective defenses deployed sooner rather than later. With that, thank you for your time. It's dangerous to go alone. Use Signal, use Tor.